Okay, good afternoon, everybody. Let's get started. So welcome to the latest edition of the UK Acoustics Network webinar series. So thank you to everyone at the UK Acoustics Network, in particular Zoe, who's on the call for facilitating this event. To introduce myself, my name is Bryn Davis. I'm a postdoctoral research associate at Imperial College London. Here I'm working in the research group of Richard Cruster, who I'm sure many of you will know. And before I was here, I was at ETH, where I worked with Habib Murray. So broadly speaking, I study wave propagation in microstructured media, and then related applications and exotic phenomena. And I mean, the kind of the umbrella term for all these scattering objects that I'm studying is this buzzword, metamaterials. And so in the next 45 minutes ago, I'd like to give you a sense of this work. In particular, I'm going to take the approach of first introducing an asymptotic method, which we developed with the group in Zurich. And then, in order to demonstrate its versatility and usefulness, I'll use it to study a few different examples. So one of these will be the design of structures that have tunable topological edge modes. And then the others will be a design of bio-inspired wave filtering devices, and also the design of subwavelength sensors who have this enhanced response based on having exceptional points. But more on that later. I should add that the various results I'm going to talk about are drawn from collaborative works with the likes of Habib Murray, Eric Kiltunen, Hyundai and Sankin Yu, who most of whom at some time or other have been colleagues of mine in Zurich, but are now spread all over the world. So the format of the next hour or so is going to be that I'll talk for around 45 minutes. If you have questions that come up during that time, then please put them into the Q&A function of this Zoom webinar. And then in the time at the end, we will go through them. If you have any issues during the call, then feel free to use the chat. In particular, Zoe's here from the Acoustics Network to monitor anything that comes up. So with that, let's get started. So let's briefly go over some context. So the properties of these metamaterials that we're going to study will rely on the fact that they're composed of these resonant elements. So they're composed of some repeating units which act as subwavelength resonators. That is, they experience resonance in response to wavelengths that are much greater than their size. And this is a powerful and at times somewhat counterintuitive phenomenon, which, as we'll see, requires the use of sophisticated mathematical techniques in order to understand it fully. In the setting of acoustics, the classical example of subwavelength resonance was observed in the early 20th century by Marcel Minut, and it came about through his work on trying to understand the acoustic properties of air bubbles in water. He did this by conducting a series of experiments that looked something like the following. So you've got an apparatus for releasing air bubbles, a little air bubble here into this water bath. And then his experiment was that he would listen to the pitch of the sound that this bubble was making. So he's doing this by ear. He'd judge the pitch and write it down. He then used this apparatus at the top to catch the bubble, from which he could measure its volume. And he derived formulas relating the pitch and volume of the bubble. And what he showed and what led to the work that ultimately got to what we're studying now is that these air bubbles resonate with a wavelength that is much greater than their size. And now this phenomenon is not only interesting and eye-catching, but this property, that air bubbles act as very strong scatterers even at very small scales, mean that they can be used as the building blocks for much larger, more complex structures. So For example, this is the experimental setup from this team at the University of Manitoba. And they were able to reproduce this exotic scattering behavior by injecting gas bubbles into, this is a polymer-based gel, the relatively high viscosity of which means the bubbles hold their shape, and so we can start to design complex structures with a variety of exotic properties and applications. And as I said, these complex microstructured materials are examples of what are commonly referred to as metamaterials. Metamaterial being a broad, perhaps slightly vague term that encompasses a variety of structures and is admittedly difficult to define precisely. So a quick look at Wikipedia with a valuable starting point is suggests that metamaterials are those with somehow supernatural properties. And the entry goes on to observe that metamaterials typically feature a repeating microstructure, and that this repeats at scales that are much smaller than the operating wavelength. I think the definition of Graham Milton and colleagues is also insightful, and they add this notion that a metamaterial is one whose top-level structure means it exhibits properties that go beyond those of the ingredient materials. So somehow really the structure, the long-range structure that gives you these exotic properties. And this is really witnessed by the setting that we're studying, because a single bubble arguably is not really useful, but once you put them together to build complex, intricate structures, then, as we'll see in the next few minutes, you can start to achieve very useful effects and phenomena. And these attempts at definitions are perhaps clarified by looking at some of the classical metamaterial examples. So really kind of some of the seminal work in this modern study of metamaterials was the development of materials with effectively negative refractive indices. And with this in hand, researchers were able to go on to develop quite high-profile devices such as perfect lenses, cloaking and shielding devices. And then since these groundbreaking discoveries, approximately 2 decades ago, the field has expanded very rapidly. And it's worth highlighting that acoustic metamaterials in particular are very close to commercial application. And some will argue this is perhaps where the future of this field really lies. Just to pick up on one example, here's an example of a metamaterial developed by Nissan. They shared last year, and it's a honeycomb structure that's designed to act as a very effective yet lightweight broadband sound insulator designed to reduce road noise in cars. And so with this in mind, we're going to study the following mathematical problem. So we have some disjoint union of material inclusions whose material parameters are highly contrasting with those of the background medium, as was the case for air bubbles in water. And our aim is to derive a first principle method for characterizing this structure, but we'd like this first principle method to be sufficiently concise and easy to work with, that we can use it to study a range of interesting and useful applications. And with that, the structure is going to look like so. So I'll start with the asymptotic methods. This will use boundary integrals, and will characterize the resonant states of this structure in terms of the eigenstates of a matrix. Then we'll look at some applications. The first will concern the design of bio-inspired metamaterials based on the Cochlear. The second will be an analysis of active metamaterials, which can be designed to have higher order resonances such that they have applications in sensing problems. And then finally, we'll look at periodic structures and design robust and topological waveguides. So this talk is going to be quite compartmentalized. into distinct parts. So if I lose you at some point, there'll be lots of opportunities to jump back on board. Okay, so let's get started. So as I say, we're interested in studying scattering by this disjoint collection of material inclusions, which represent our resonators. We're going to study a Helmholtz resonance problem like so, which has transmission boundary conditions on the boundaries of the resonators. The point to highlight here, or a point to highlight here, the appearance of these delta parameters, which appear in this continuity of flux condition. And these will be crucial because these will be our asymptotic parameters. So in the case of, in the acoustic case, these correspond to the ratio of the density of the material inside and outside the resonators. So for example, go back to this example of air bubbles and water, this ratio is the value on the order of 10 to the minus 3. And so now there are a variety of methods we could use to attack this problem. Classical approaches tend to depend quite heavily on the shape of the resonators. So for example, if we restrict ourselves to circular or spherical inclusions, then we can deal with these very nicely using appropriate coordinate systems. If we want to handle more general shapes, then equation methods, integral equation methods are popular. Today we'll use boundary integral formulations, but volume integrals are also widespread. And in both these cases, the key realization is that what we're doing is recasting this differential problem as a nonlinear eigenvalue problem, the analysis of which falls into this nice, quite general theory of characterizing scattering resonances as poles of what will turn out to be meromorphic operators. That's something we'll take advantage of. The other key thing that we will exploit is that we want to capture the subwavelength behavior of the system. And in this case, there are, again, some classical approaches. So, for example, a standard thing would be to perform asymptotics in either the limit of low frequency or small particle size. And by extension, homogenization techniques are also commonly applied. In this work, we are going to take a very slightly different approach and instead consider an asymptotic limit in terms of these material contrast parameters, which we control with this single delta. And this will be our asymptotic parameter. And then subsequently, we'll define the notion of subwavelength resonance to be a resonant frequency that depends continuously on this parameter delta and converges to 0 as a function of delta going to 0. And the advantage of this approach is that when delta is 0, the limiting problem is, in a sense, non-trivial. And I mean that in the sense that it has non-trivial resonant solutions, a space of solutions that we can understand. And then we're able to study the system for small non-zero delta as a perturbation of this state. And so with this, we see this reveals the mechanisms that make this subwavelength resonance really kind of fundamentally different from, shall we say, typical wavelength type resonance. This approach will also allow us to understand the near field behavior of a system of resonators fixed position and size, which will be important for what we want to do in a moment. So the key notion that will come up when we do this asymptotic method will be this idea of capacitance. And so this is a concept lifted directly from electrostatics. So for a system of material inclusions in 3 dimensions, we define so-called capacitance coefficients like so. So this is a set of integrals on the boundaries of these resonators involving the Laplace single layer potentials, which is defined like so. So this gives us a square matrix whose dimension is equal to the number of resonators, the number of material inclusions. And these quantities have been studied, as I say, extensively in the setting of electrostatics. where they were first introduced by Maxwell, and are used to relate the distributions of potential and charge in a system of conductors. In our setting, the intuition is similar. However, the quantity that we're interested in is what we'll refer to as the generalized capacitance matrix. So it's this matrix with this additional weighting at the front. This weighting accounts for the denominator accounts for the different sizes of the resonators, and the numerator accounts for the different material parameters on each resonator. So the main results of our analysis look like so. So at the top, we're just recalling the definition of subwavelength resonance as this asymptotic, in terms of this asymptotic condition. And if we do so, then we have firstly this result, which says that if you have a system of n of these resonators, so n of these material inclusions, then there exist n these subwavelength resonant frequencies with positive real parts. That's already nice. It's nice to have this existence result. And then given their existence, we can compute asymptotic formulas for their value. And it turns out that in the three-dimensional case, if we find the eigenvalues of this generalized capacitance matrix, then they determine at leading order the resonant frequencies. It's worth noting that this capacitance matrix, as you recall from the previous slide, has these deltas in it, and so these eigenvalues scale like delta. So omega leading order scales like the square root of delta. And we can also, if we want to keep going with this method and compute higher order terms. So here I've stated it just for the case of the resonators all having the same material parameters, so the same wave speeds and the same contrast parameters. In which case we get leading order part is from this eigenvalue, and then the subsequent order comes from this, what involves this quantity here. It's worth noting that if these wave speeds and these deltas, the contrast parameters, are real values, then lambda is real, and this quantity tau is also real. It's real and it's also non-negative. And so we can interpret this as the leading order gives the real part of omega, and then the next order gives the imaginary part of omega. And then if we look at this plot on the bottom, we can compare the asymptotic approximation, which is the squares, with the numerical values of the resonant frequencies. Here we're doing it for an array of spherical resonators. And we see good agreement, but with a significant reduction in computational time. And this is really one of the big consequences of this theorem that will be very useful for us in the application that's coming in just a moment. Because when we're approximating these frequencies using the generalized capacitance matrix, even though we still need to use some at times reasonably hefty numerical machinery to compute the generalized capacitance matrix. For instance, here we're using just a multipole expansion. You could use boundary elements or other things as well. The fact that we've removed the need to do any numerical root finding is the reason that we have this significant reduction in computational time by several orders of magnitude. And then the final point to make before we move on to applications is that not only is the resonant frequency determined by the eigenvalue of this capacitance matrix, but the associated resonant mode is determined by the associated eigenvector of this matrix, that is the VNs. And so what we've done here is we've done first principles asymptotic analysis, which comes with explicit error terms, and found a result that characterizes in an intuitive way the behavior of an n-body system in terms of the properties of an n by n matrix. And this is sufficiently intuitive and easy to work with that we can readily use this theory handle a variety of applications, some of which we will examine now. So the first of which is going to be the design of Cochlear-inspired metamaterials. So briefly, some background. So the Cochlear is this spiral-shaped organ that's located somewhat deep inside the head, and it's really the center of human hearing. It's here that sounds are filtered according to frequency. So high sounds experience lead to a response at one end and lower sounds at the other. And then following this filtering, these vibrational waves are converted into neural impulses by receptor cells, and these impulses are sent to the brain. And so there's this large community working on graded metamaterials, and out of that have emerged some attempts to design biomimetic metamaterials that mimic cochlear function. These devices have been somewhat wide-ranging, but are all based on graded arrays of resonators. So examples at the top have some ducts with a graded array of Helmholtz resonators coming off them. Next two examples I've picked out are abstract examples, where I've got a mass spring system here and an array of vibrating reeds. At the bottom here we have a photo from an experimental work where they're using quarter wavelength pipe resonators, again with a gradient. And the subtlety here is that they've added, you can see the wires around the back of the picture here. So they've added microphones and speakers to the ends of some of the resonators. And this is allowing them to add amplification routines into this metamaterial, making it into an active metamaterial, which it turns out is a feature that Cochlear has, is increasing the closeness with which the response of this artificial device matches the cochlear. And more on that in just a moment. So using our asymptotic approach with this generalized capacitance matrix, we can likewise take a graded array of resonators and study its properties. In particular, we can choose the setup, the configuration of this structure to be such that the response, in simple terms, matches the response of the cochlear. In particular here, we're matching, on the x-axis, we've got the position of maximum excitation. So this is distance from the start. How far along does the peak response occur? And we're comparing that to the frequency of the incoming wave. And here the red line is the relationship that exists in the cochlear. And what we've done is we've fitted the geometry of the structure such that the resonant frequencies of this resonator array match the response that's observed in the cochlear. When you do this, you notice some other things. So you also notice one, for example, if you look at how the scattered field evolves as a function of time, then again, this shares some characteristics with what takes place in the cochlear. So this transmission peak moving from left to right, so from small to big through the array, slowing down and decreasing wavelength up to some position of maximum response before then decaying, is really characteristic of what people see when they study the response of the cochlear membranes. And so going beyond this, one of the nice things about having our analytic framework is that within our abstract model, it's quite easy to play around with all sorts of things. So for example, one thing we can do is we can model the introduction of amplification to the system. And so this, as I mentioned a moment ago, when mentioning the experimental work, this mimics the action of the cochlear, which is not a passive sensing array, but has active elements containing motor proteins and uses some kind of amplification mechanism the details of which are a quite significant open question. And then within our model, we can experiment with different nonlinearities. So for example, we can take this Hopf type nonlinearity. This experiences a Hopf bifurcation at some critical value of this parameter mu. And then we can explore how the system behaves in this case. So for example, we can right here look at some phase space diagrams and verify that the system is stable. And then on the left, we can look at the amplification expressed here as a function of the forcing frequency. And one of the things here is we've plotted it for 3 different amplitudes, 3 different volumes of sound. This is the loudest at the bottom and the quietest at the top. And this demonstrates one of the really crucial reasons that this nonlinear amplification is important to us humans, because it means that quieter sounds are amplified much more greatly than louder ones. And this allows humans to hear sounds over a very wide range of volumes relatively efficiently with a kind of a compressed encoding. And so what we have here with this Cochlear-inspired metamaterial is a physical structure that is designed to filter sounds in a way that replicates how the human ear does it. And so an observation is that there's also this very large world of signal processing where people are trying to design algorithms that do, I claim, more or less the same thing, replicate how we hear fundamentally. And so our idea has been, given that we have a model that a nice asymptotic method for describing how our structure behaves, use this as the starting point for deducing bio-inspired signal processing algorithms. And so a very brief observation in this direction is that the scattered field looks like so, at least at leading order. And this is spatial eigenmodes with time-dependent coefficients, which are given by the convolution of the incoming field with some kernel function. And these kernel functions, it turns out, are first-order gammatones. So they're sinusoids multiplied by some window that is a gamma distribution. And this is particularly nice and eye-catching because several other studies, both biophysical studies and numerical studies, have also pointed towards these convolutional decompositions with gammatone kernels as being very effective for mimicking human auditory processing well. So that was a nice observation. And then we kind of ran with this principle of biomimicry in mind. And we said, try to establish additional processing stages that mimic the ability of humans to, so for example, not only identify features of sounds locally in time, but also to recognize long-range global structures and indeed statistical properties of a sound. So in particular, just to pick up on this example, humans are known to be well adapted to hearing a class of sounds that's often known as natural sounds. This is maybe arguably a slightly misleading name, because what I'm referring to here are behaviorally significant sounds, which, at least to me, I define as satisfying these observed statistical distributions, which are depicted here. So this is actually a recording of a trumpet playing, from which we can extract certain statistical properties, the details of which I don't want to stress today, other than trying to convince you that we can fit curves with the following descriptions to them, from which we deduce some relatively small collection of parameters that describe these distributions. And so the idea is that these parameters, which describe these distributions, give us kind of a ready-made low-dimensional representation of the global properties of a sound. And further, this is obtained in a way that in some sense mimics how humans do it. And so, just briefly, with this in hand, we've done some initial tests to explore the extent to which these parameters are useful for classification. So here, musical instrument classification is what we tried. Success rate of just over 30%. It's perhaps not particularly eye-catching, but I think to emphasize here is we're just using these, so 6 of these global parameters as our vector to use for classification. And these are just global parameters. So really, we probably couldn't expect much more than a much greater success rate than this. And so the reason this is eye-catching, the reason I'm sharing it is that to us, what this shows is that these quantities contain something significant. And exactly what and how we can use these to, for example, solve this classification problem more effectively or more efficiently is an object for future investigation. And so I'd like to just briefly finish this little section on bio-inspired metamaterials by looking at this sketch of the biomimetic workflow that we have in mind. So biomimicry, to be clear, has been this practice of taking advantage of nature's remarkable ability to devise innovative solutions and then take design inspiration directly from these solutions to solve challenging problems. And I claim that our asymptotic method is facilitating this kind of 3-way exchange of ideas and concepts between, on the one hand, biological systems, also acoustic metamaterials, and signal processing algorithms. Okay, so I'd like to move on to another example, which is the use of active metamaterials in the design of so-called enhanced sensors. So the idea here is that we want to be able to detect small local perturbations. So for example, if you have the presence of some small particle, this particle might be, say, a virus, for example. You want to detect whether or not this thing is present. So typically, the appearance of this small object would cause a shift in the resonant frequencies of this array that is proportional to the strength of this perturbation. So in the case of a small particle, proportional to its size. And that's this blue line here, the linear shift. But the idea of what we want to do is to design an array for which this shift is enhanced, particularly for small perturbations. And the way we're going to do this is by adding sources of energy gain and loss to the system, and then fine-tuning the parameters accordingly, such that we have exceptional points. And devices based on these principles have been designed and implemented. For example, here in the setting of photonics, we have a 3-resonator system. They've used heating elements to add gain and loss on either side, and then you see that we have this kind of enhanced response that we were looking for. And so the fundamental result at the heart of our analysis is the following, which is quite wordy, but to put it simply, it says that if a system's Green's function has an nth order singularity, and then you introduce a small particle nearby, then one of the eigenfrequencies will be perturbed with magnitude proportional to the nth root of that small particle's volume. So if the particle is small, this perturbation will be very large. And then just briefly, this constant e to z is clearly significant, and this depends on z, which is the position of this small particle. And so with this in mind, our aim is to design systems with these nth order singularities. And one reason for these singularities to occur is the existence of an exceptional point. So an exceptional point is a point in parameter space at which the eigenvalues and the eigenvectors of the system simultaneously coincide. And these are a consequence of balanced symmetries in the system, and hence a standard approach is to look for them in systems that already have some underlying symmetry. And so, for example, in systems with parity time symmetry. So this photonic example from a few slides ago is symmetric, both in the sense there's a symmetric geometry, and you've got gain on one side and loss on the other. People also commonly study symmetric Hamiltonians, and in the case of acoustics, people have tried to implement gain and loss into acoustic settings, and thereby find exceptional points. Within our framework, our generalized capacitance matrix-based framework, the crucial realization is that our analysis allows us to have complex valued material parameters. So this factor that we added in front of the capacitance coefficients can be complex valued, no problem. And so we can use the generalized capacitance matrix to look for coincident eigenvalues and eigenvectors in the case that we add gain and loss being represented, albeit in a slightly abstract way, by these non-zero imaginary parts of the material parameters. The crucial realization when you do this is that the general capacitance matrix will be non-Hermitian, and thus we can hope to find these exceptional points. One subtlety to highlight is that in our setting, we're actually finding asymptotic exceptional points. So these are points at which the generalized capacitance matrix has an exceptional point, meaning the full differential system has an exceptional point at leading order in delta. And I should add that this is not a weakness of the analytic approach, but represents the behavior of the system that we're modeling, a consequence of the fact that the radiation condition, we're studying the resonators in an open system, and the radiation condition means that the symmetry we impose on the resonators is not extended to the far field, meaning that we don't have exact degeneracy of these exceptional points. When we do this, we can find a symmetric system of two resonators like so has an asymptotic exceptional point, and indeed we can compute the appropriate parameter values. It's informative to plot these values. If we do so, this is done numerically, we see that there's an asymptotic exceptional point somewhere in the middle here. As this is the real part at the bottom and the imaginary part down here. In this case, the asymptotic parameter is on the order of, so this delta is on the order of 10 to the minus 4. And as a result, this error, this asymptoticness of the exceptional point is small enough that we still get this enhanced, the desired enhanced sensing response. Now, this is nice, but we want to really, given that this enhanced response has n as an exponent, n being the order of the exceptional point, we naturally want to try and find higher order exceptional points. And to do that, we need to study a larger system of resonators. And then our approach to doing this, in order to make the capacitance matrix easier to work with, was to make an additional assumption, which is an assumption that the distances between the resonators is relatively large compared to their size. The reason this is nice is because in this case, we can compute explicit leading order expressions for the capacitance coefficients, and so our analysis just becomes that bit more efficient. And in particular, we can do when we come to very large systems, as we will in like 2 slides time, we can do very efficient numerical searches for these exceptional points. We can also just start with a system of 3 resonators and find there is a system that there is an exceptional point of order 3. given we can compute its parameter values and corresponding frequency. We can do the same plot as we had for the case of two resonators. On the left, we have the resonant frequencies of the full system, whereas on the right, these are the eigenvalues of the capacitance matrix. So you can see that we have in the middle here exact degeneracy for the capacitance matrix eigenvalues, but only an asymptotic one for the resonances of the differential system. And so we can run with this and look at very large systems. So while a system of three resonators had one third order subwavelength asymptotic exceptional point, a system of four resonators turns out has four parameter values that give rise to such points. Here, to give you a sense of the symmetry, I'm plotting the imaginary parts of the material parameters at each of the 4 points. And so what's nice to see here is that each one has a different underlying symmetry, so captured by the relative magnitude of the quantities. So remember that we're assuming the system is symmetric, so it will always be symmetric on the center line. And then each one of these four has a different combination of relative sign and size of these two values. And we can run with this even further and consider this symmetry pattern continues to even larger systems. So for example, here we take two of these fourth order exceptional points and show that in systems of 8 and 14 resonators, there exist exceptional points with the same symmetry. And so for very large systems, the number of exceptional points grows very quickly, and it becomes a challenging problem to find them. However, the value of this generalized capacitance matrix approach is that the behavior of these intricate subwavelength resonator systems has been reduced to just a matrix eigenproblem. And so we can attack this with all the conventional methods and to efficiently reveal this interesting and otherwise difficult to understand behavior. Okay, so in what time I've got left, I'd like to move on to one final thing, which, in what I've presented so far, we've seen methods for designing very precise structures that achieve specific and useful effects at subwavelength scales. However, building these small, intricate structures is quite difficult, and so it's important that the properties of our designs are robust with respect to random errors and imperfections in their design, or design and manufacture. And so to finish, I'd like to look at some of the techniques and ideas that are available in regard to this robustness, and the setting to demonstrate this is that I'll use is that of periodic waveguides. And so there's a guiding principle at play here, and this says that if you have a periodic structure and you introduce an error or a perturbation at some point, then certain frequencies will be localized in the region of that error. And so that's what we see. That's what we see here. We have this is a structure where we've changed, or my colleagues in this 2018 work have changed the size of one of the resonators in this repeating array, and you see the x-axis is a different scale here, but you see there is an eigenmode that is localized in a region of this defect. However, if we look at the spectral properties of this, we have here the frequency of this localized mode shown in red, and it's only a small distance away from the continuous spectrum of the original periodic operator. In fact, this distance is exponentially small as a function of the perturbation that we make to the size. And this is worrisome because it means that as soon as you introduce errors or imperfections to the structure, this red localized frequency is liable to be lost amongst this continuous spectrum, and correspondingly this nice localization behavior will break down. So what we'd like to do is to make this localized frequency be further from the continuous spectrum. And the fundamental principle that's often applied in this field of topological insulators is that if you put two, shall we say, topologically different materials side by side, then this interface supports edge modes, and these edge modes will be more robust with respect to perturbations. Indeed, they're said to be topologically protected. This has been, there's a very large active community studying this in a variety of settings, but it first rose to prominence in quantum mechanics, but has since been observed in a wider range of settings, including acoustics and photonics, just to name some. The references listed here are intended as a starting point for anyone new to the field, and by no means exhaustive, or frankly, neither are they representative of what is a very large and active field. So if we look at a chain of resonators like so, then we can take our previous analysis for finite structures and modify it by switching the Green's function. And in doing so, we obtain a decomposition for the spectrum of this periodic operator in terms of these modified quasi-periodic operators, where this quasi-periodicity parameter alpha varies over the Brillouin zone. So this is just standard flow K theory, those who are familiar. And so with this method, we can obtain a result that's directly analogous to what we had in the finite case, which characterizes the subwavelength resonant frequencies in terms of the eigenstates of this quasi-periodic generalized capacitance matrix. In the case of this repeating unit cell of two resonators, this matrix is a 2x2 matrix. And so the point to make here is that this asymptotic method we discussed in the case of finite structures can be directly translated into the setting of periodic structures. And with this approach, we can do another useful thing, which is to compute the topological indices associated to the structure. And so when I said a moment ago that I wanted to juxtapose two topologically different structures, what I meant is two structures associated to different values of a topological phase. And in the case of 1D periodic structures, kind of the canonical example is the Zach phase, defined like so. These are integrals involving the eigenmodes. And what we can show is that this takes the value either 0 or pi, depending on the relative sizes of these two distances, d and d prime. And it's worth noting, in the context of this talk, that this result, the Zach phase, is given by the change in argument of the off-diagonal entry of the capacitance matrix. So again, these capacitance coefficients are really characterizing more or less everything about this structure that we're interested in, at least from a wave scattering perspective. And so the end goal of this is to design practical structures with finite dimensions that can perform robust wave localization. So here we've got an array of 41 resonators, which corresponds to having different values of the Zach phase on either side. And what you see is that we have very strong wave localization around this defect, and this localized frequency, shown in red, exhibits very good stability with respect to errors. So what we're doing on this plot is, well, on the x-axis, we're increasing the size of the errors that we're adding to the positions of the resonators, and you see that the localized frequency stays nicely localized in the middle of the band gap. And so this idea of wanting to put frequencies in the middle of the band gap is something that we can pursue further, and establishes a workflow for trying to create localized modes with tunable properties. So for example, you can observe what happens when you take a periodic structure which has a subwavelength band gap and introduce a dislocation. And what we see is that this dislocation causes a resonant frequency to enter the band gap from either side. And as this dislocation becomes large, the two mid-gap frequencies converge to some single value within the band gap. The consequence of this, of course, is that it means that we have a way to put a localized frequency at any desired position within the band gap. We can study this numerically, but also analytically. So we did that using the method of fictitious sources. A little short on time, so I won't stress this too much, but the idea is that we can notice that when we dislocate the structure, it will repeatedly line up with the original structure. And it turns out that what we can do is we can replace the resonators, but replace them with source terms, F and G posed on their boundary. And then it's possible to choose these sources such that these two problems have the same spectrum. And with this, we can go along and analytically show the behavior of the curve at these points. And then all that remains is to kind of fill in the gaps, fill in what happens at the small values of D, for large values of D, and indeed in the middle, giving us a result like so. And it's worth highlighting that these results are analogous to some shown previously for Schrödinger operators with dislocated periodic potentials. And that was our inspiration. Although, of course, the physics is a little different in the case of resonator arrays, because when our structure is not periodic potential, we don't periodically recover the initial configuration. Just to finish, this is my final slide. We can, again, given this analysis of an infinite periodic structure, we can look at some simulations of the finite equivalent of these structures. So here is a very simple example. We have the frequencies for just 6 resonators with some dislocation length D. And you see they have the expected, as D becomes large, you have the expected pairwise convergence. Bottom left here, we have the plot like we had for the previous structure, where we have increasingly large errors on the x-axis. And we see that the frequencies in the middle appear to be somewhat more stable. And the most interesting one, I think, is this plot on the right, where we're adding random imperfections with constant size, but increasing the dislocation length. And what we see is that there appears to be, so not only are these frequencies in the middle somewhat more stable, but there appears to be some sort of position of optimal stability in the middle here. So the frequency here is really not varying very much. And actually this corresponds, roughly speaking, to when the frequency is in the middle of the band gap. And this demonstrates the value of this result, because it's allowing us to fine-tune, and dare I say, even try to optimize the properties of these subwavelength waveguides. So that brings me to the end. To summarize, I'd like to briefly reiterate the fact that these different applications of high contrast metamaterials that we've been discussing are all based on this same asymptotic method, which is this characterization in terms of the generalized capacitance matrix. So I hope this convinces you that this is a versatile and useful, insightful approach. So before I look at the Q&A to see if there are any questions, I'd like to once again thank the Acoustics Network for hosting this webinar. I'd also like to have a cheeky plug for another EPSRC funded network, which is the Metamaterials Network. So if you're interested in hearing more about metamaterials in settings beyond acoustics, I encourage you to, if you haven't already, come join us and see what's going on. So with that, I will stop there.